Okay, in here they talk about what's called an asymptote. Okay, let me go back to my picture that I drew so you can see that. In this case, we do have an asymptote. In this case, the asymptote is right here. I'm going to change the color of this in a moment. Okay, so make this bright red, and we'll make it pretty thick so you can see. In this case, the x-axis is also what we call an asymptote. An asymptote is a line usually. There are things that can function the same as asymptotes that are not lines, that are curves, but you won't be dealing with them in the course that I'm making this video for. But it's this line that you are getting infinitesimally close to, but you don't actually touch it. You can touch it in some cases. In this case, you don't. But what's important is that as you go further and further in some direction, you get infinitesimally close to it forever. So to give you an example of a case where where you can cross it, but what's important is that you're getting closer and closer and closer to it, is let's say instead we had, okay, let's say this is the x-axis here. We won't worry about the y-axis right now. Okay. And let's say our function, in fact, this doesn't have to be the x-axis, it just can be any horizontal line, okay? And so let's say our function is doing something like this as we go toward the left. Right, we're crossing it, but the thing that actually matters is not that we're touching it. What matters is as we're moving to the left, you're never very far away from it, and that maximum distance between the curve and the asymptote in this case is getting smaller and smaller and smaller. Okay, so here we started off with a distance that's pretty far from the line, and then it got smaller. Okay, and then if we go here, let's say, we're even smaller, and then if we go here, it's so small you can barely see it, and you so on. Okay, off to infinity. So in this case, and in the case of our function f of x equals 6 to the x, as x approaches negative infinity, f of x approaches 0. So let's write that down. So approaching negative infinity just means getting infinitely negative, right? Infinitely small. So as x approaches negative infinity, 6 to the x approaches 0. And so what that means is, since 6 to the x power is our y value, that means y equals 0, right? That's where we're approaching, is an asymptote. And because it's a horizontal line that we're talking about, it's called a horizontal asymptote. It may seem like this is a pretty strange phrase to say out loud, horizontal asymptote. Asymptote on its own is already a bit of a strange word to a lot of people, but there are more types of asymptotes than this, so that's why we call it a horizontal asymptote. There are vertical asymptotes, there are slanted asymptotes, and then, like I mentioned earlier, there are things that aren't even lines that can function like asymptotes. Okay, let's go back to the book here. Okay, what they've done here is they've summarized the general case when your base is greater than 1. Right? The base can't equal 1, but it could be smaller or bigger. Well, if you restrict it to just the cases when your base is bigger than 1, your graph is always going to look something like what you see here. It's going to have this general shape. It's going to cross the axis at 0, 1, because a positive number raised to the 0 power is 1. As you move to the left, it's going to be 1 over your base, and then 1 over your base squared, and then 1 over your base cubed, and so on. And as you move to the right, it's going to get bigger and bigger and bigger. You're going to start with the actual value of your base, and then your base squared, and your base cubed, and so on. This is what we call exponential growth. So f of x equals 6 to the x is an example of exponential growth. Okay, in everyday English, when people refer to growing exponentially, they generally just mean it's growing fast. But we mean something more than that. We mean that as time, or whatever your x-axis is representing, as that increases, your outputs, your y values, increase by constant factors. Okay, in this case, that constant factor is the base. So in our case, if you moved 1 unit to the right, you had to actually move 6 times higher for your y coordinate. So not 6 units higher, 6 times higher. So with lines, with linear equations, you increased by constant sums. Okay, you kept adding the same amount. This time you multiply the same amount. Okay. Now, the book switches over to talking about base values that are still positive, but now less than 1. Okay, they show 1/2 and 1/3, and they want you to try 1/4 and 1/5. We could do 1/6, but I don't really want to because it's too similar to what we've done previously. So instead, what I'm going to do is I'm going to pick 1/4 here, and I'm just going to change it to 3/4. Okay, because that's still something between 0 and 1. Okay, so A equals 3/4. So this time, just so that we differentiate it from what we did before, I'm going to use G. So G of x equals 3/4, and we want this whole thing raised to the x power, so I'm going to put that in parentheses. Okay, so interesting. I don't know why it's freezing on my screen like this. Hopefully it doesn't do that some more. But anyway, let's fill out a table of values. Okay, as before with our function up here, f, the domain is still going to be all real numbers. And so I am, again, going to pick a range of values. And so I'm going to include positives and negatives, just like we did before. But I'm also going to throw in a 1/2 and a negative 1/2 in there, just so we can address that along the way. So I'm going to do -2, -1, -1/2, 0, 1/2, 1, 2. Okay, as before, I'll start with 2 because, again, that's the one that's most familiar to us. So 3/4 squared. Well, that's just 3/4 times 3/4. So that's 9/16. Okay, next one, right above that, 3/4 to the first power, that's just itself, 3/4. Next one, 3/4 to the 1/2. That means we're taking a radical of 3/4. What this is going to be is you're going to have a radical 3 over the radical of 4, which is 2. Radical 3 is an irrational number, so there's no real simpler way to write this, but we can approximate it. So if I take the radical of 3, which is approximately 1.732, okay, and I divide that by 2, I get 0.866. Okay. Over here I have 3/4 to the 0 power. The positive number raised to the 0 power is 1. Next, 3/4 to the negative 1/2. Okay, this means it's just going to be 1 over 3/4 to the positive 1/2. Okay, So what that means is it's going to be the reciprocal of this one here. So it's going to be 2 over radical 3. Okay. I don't know if everybody reading this will have practiced rationalizing the denominator, so I won't do that. I won't assume that you already know that. So we'll just go ahead and put this in our calculator. Okay, make sure we have parentheses in the right spot. Okay, this is 1.1547, so that would round up to 5. Okay. Almost done here. 3/4 to the -1, well, that would be 1 over 3/4 to the first power. Well, that's just going to be the reciprocal of 3/4. This is 4/3. Okay. And finally, 3/4 to the -2. This means we're going to have 1 over 3/4 squared. Well, 3/4 squared was 9/16. And so we have the reciprocal of 9/16, which is 16/9. Okay. For those of you that don't really like thinking about these improper fractions, you can convert them to decimals if you want. You can also look at them as mixed numbers. I'm just going to make a little note over here that as mixed numbers, this would be 1 and 7/9. Okay, so getting close to 2. Whereas this one here, the 4/3, that would be 1 and 1/3. Okay, so a lot closer to 1. Okay, so we're going to graph this. I am going to, again, give myself a pair of axes to work with. Okay, it's a little off, so let's move this just slightly. There we go. Okay, this time I don't need to fit nearly as much in. Okay, 9/16, that's not even a 1. 16/9 is not even a 2. Okay, so we don't really need to get that far. So what I'm going to do is I'm just going to go up to 2 in each direction. Okay, so let's see, if I have 1, 2, 3, 4, 5, let's go by fifths. Okay, and then so that's 1, 1, 2, 3, 4, 5, that's 2, and so on. Okay, I don't really care about showing 3, but I'll show it because it's here. 1, 2, 3, 4, 5, 1, 1, 2, 3, 4, 5, 2, 1, 2, 3, 4, 5, 3. And so on, 1, 2, 3, 4, 5, -1, 1, 2, 3, 4, 5, -2, 1, 2, 3, 4, 5, -3. And then finally, 1, 2, 3, 4, 5, -1, 1, 2, 3, 4, 5, -2, and 1, 2, 3, 4, 5, -3. Okay, so let's plot some points here. Okay, so let's start over here, -2. We want 1 and 7/9. Okay, so right here, this point for our y value, this would be 1 and 4/5, in other words, 1.8. Okay, 1 and 7/9, if you want to think of it as a decimal, that's about 1.7778, let's say, round it there. The point is it's going to be pretty close to that. Okay, 7/9 is pretty close to 4/5, is what I'm saying. So -2 is going to be just under that right there. Okay. Next up, -1. That's 1 and 1/3. Okay. Well, if I get rid of the guidelines here, it's a little bit easier to figure this out, because sometimes looking at the points at fifths can screw me up. Okay. But if I look at it without the grid, we can divide it up like that. Okay. One of the advantages to doing things on a computer is you can delete your background and then bring it back. So -1 is 1 and 1/3 for the output, so we're looking at about right here. Okay. Negative 1/2, so that's halfway between right here, is approximately 1.155. Okay, now again, this mark right here, we're looking at fifths, so that's 1.2. So it's a little bit below that. Okay, so we would be about right here. Okay, 0 for our x-coordinate has 1 as the y-coordinate. Okay. Positive 1/2 has an output of 0.866. Okay. Here would be an output of 0.8, so 0.866 is a little bit higher. 1 goes to 3/4. Okay, so here's one again where it's a little bit easier to work with if I get rid of my background. Okay, so here's a half, and then if I split each of these in half, I have fourths. Okay, so we have 1 as our input is paired with 3/4 for our output, so that's about right here. Okay, and finally 2 as our input corresponds to 9/16 as our output. Well, 9/16, that's very close to 8/16, and 8/16 is 1/2. Okay, so 1/2 is right here, and it's just a little bit above that. Okay, so looking at this, since my dots aren't totally uniform in size, it looks like it wobbles a little bit, but what we're actually getting is it's a slightly curved line, slightly concave, I should say, curve. There we go. Okay, and you might think, wow, that looks a lot different than what we saw before. Okay, but that's only because we're zoomed in. Let me show you what happens if we zoom out. Let's go back to Desmos. Okay, let's get rid of all these. Okay, and let's see, I want to go back to something pretty standard. So let's do -10 to 10 and -10 to 10. Okay, so I'm going to change this from 6 to the x to 3/4. There we go. And so look at how different this looks than our other version. Okay, now it wouldn't look so different if I zoomed in. Okay, if we zoomed in, sure, that looks about like what we had before. But when we zoom out, we can see, oh wait, this looks very similar to what we had before. It's just a reflection.